Welcome to my presentation on predictive maintenance. I start with some context and chances. We know that data-driven approaches offer new business opportunities. Many of them are already known. If I buy something with my credit card, this information is first sent to a data center where the credit card operator checks whether I bought something or maybe a criminal. We can store all data of our customers and visualize and use it nicely. We can store all data related to a production chain and use this data to optimize the quality of our products. And similarly, we can use it to optimize the logistics. And the last example, which I show here, is predictive maintenance, the topic of this talk. Our predictive maintenance case, which I will show, is from SNCF, the French train operators. They want to predict faults on trains' door. SNCF bought new trains which are operated in Paris, and since these are new trains, they collect a lot of data. The objective of SNCF is to predict which trains will suffer in 8 hours on a train's door fault. And secondly, which of these train door faults will have a critical influence on the train's operation. If we can correctly predict this, SNCF will benefit from this. They can improve their maintenance. They can, for instance, disable doors proactively, and such disabled doors will not fail anymore. And finally, trains will be less delayed. We from LeanBI demonstrate in this talk how we can answer these two questions above with machine learning. We use a software from the Daiku, which I will show you in a moment. Now we are in program of the Daiku. As you can see, we can open this program in our browser. What you see here is all the path from the data to the first prediction, the prediction whether the train will experience a door fault in the next 8 hours. I zoom in a little bit. We have here the information whether a door fault happened, and here we have the data of the trains. These are messages, 1500 messages which are recorded by every train, and here we combine the data to this data set where we will have a closer look to it. We have some identification numbers here and here, the hour when the data set was collected, and then these 1500 messages from the train. For safety reason, these numbers are cryptical numbers, so we don't know exactly what the train was reporting. At the end, we have information about the weather here, the medium temperature. And finally, the weekday of the data. 0 is a Monday, 1 is a Tuesday, and so on. Then the week number, the calendar week. And finally here, the information whether a door fault happened or not. Most of the time no door fault happens. That's why we have a 1 here with faultless. Sometimes a door fault happens, then we have a 1 at fault, and even less this door fault critically influenced the train's operation, and in this case this would be indicated with a 1 here with the critical fault. So let me now visualize this data. We start with the failure door fault probability on the y-axis, and on the x-axis
the average temperature, we can easily change this to the average rain, for instance, or to the week, calendar week. We know we have 52 weeks per year, and here we see something interesting. We have these peaks of high fault probability, and the interesting fact is that these peaks are regularly every 2 months. And here the question arises to SNCF, what do you do, right? What do you do at this point in time such that the fault probability is such high? And the answer to, and we have to carefully discuss this with SNCF such that they know what they can change in order to reduce these peaks and hence reduce the probability of a door fault. This is an example where we don't even need machine learning to do something useful, but already a useful visualization is good. But now we want to do machine learning, and for this we go back to the first view. Now I used this data to train a model, an algorithm, which can predict which train will have a door fault in the next 8 hours. I can go into this model here, a logistic regression model, and have a look on which variable is how important for this algorithm. Here, these 3 most important messages have a positive coefficient and are green, which means that the more of these messages are recorded, the higher the algorithm predicts the probability that the train will have a door problem. It's vice versa with these 2 algorithms with a negative coefficient. So the fewer of these messages are recorded, the higher the probability of a door problem. And then here follow the less and less important messages. Now we can instruct the algorithm on how aggressive it should predict door faults. It can be very generously and basically predict no door fault at all. Or it can be very aggressive, very strict, and basically predict that every train will experience a door fault or something in between. But we can go now back to the value which is proposed by the algorithm. So now we have an algorithm which is able to predict whether a train will have a door fault or not. And we apply this algorithm on the data which is provided us from the SNCF, where they don't tell us whether this train will have a door fault or not, and we predict now whether all these trains have had a door fault or not. And this is our prediction. It's either 0, no door fault, or 1, a door fault. So now we've predicted or answered the first question, which train will suffer in 8 hours on a train's door fault. The second question or prediction remains to be done. Will this critically influence the train's operation? We could now approach this second question as we've done it with the first one. We could take the train data and predict. Now, a new thing, all trains with a door fault with critical influence on train's operation. Same algorithm, same procedure. The only thing we do, we choose a different column, and instead of predicting door faults, we predict critical door faults, or door faults with a critical influence on the train's operation. Same algorithm, everything the same, different column. we could do this, but this approach would miserably fail. And now we're here to solve this problem. The first thing we do, we try to solve a simpler question. We partition this question into two sub-questions. The first one is we take the train's data and predict the door faults. And the second question is we take then the predicted door faults and predict whether these door faults critically influence the train's operation or not. And the nice thing is that we already predicted or answered the first question, and the second question is the one which we will answer now, and that's a much simpler question than the previous one. So that's one thing we do, we answer a simpler question. The second thing we'll do is we have to mitigate the overfitting. Now let me lose some words on overfitting. The problem is that we have this 1500 parameters from the train, and the algorithms will struggle with this vast quantity of information, especially as we only have 50 critical door faults available to train our algorithms. So we will handpick the parameters. That's one part of the solution. And I personally believe that whether a door fault critically influences the train's operation is mostly influenced by the surrounding parameters and less by technical parameters. So it's important whether this door fault will happen in a main station or somewhere in the countryside. Or a door faults in the rush hour will influence the train's operation much more than a door fault somewhere in the middle of the night. So these parameters are important in my opinion. So we will delete all the technical parameters and only keep the rest. So we will have much less parameters. And the second thing we do is we will use selective algorithms or tune the algorithms such that they get selective, so that they only will concentrate on few important parameters and try to neglect or ignore the other ones. So now we have three things which we will do. We will answer a simpler question, we will handpick the parameters, and we will tune the algorithm such that it will be selective. And now we have a look on how we do this on Dadaiku. So now I'm back in Dadaiku. As you can see, I already prepared some steps and it's kind of confusing, but you recognize many things from before. That's the data preparation, that's the algorithm which predicts whether a train will suffer from a door fault or not. And this part here is new and we concentrate on the new part. So here we have the data with all the trains and we filter it such that only door faults remain in this SNCF fault only dataset. And now the algorithm will learn to distinguish between door faults with a critical influence on the train schedule and door faults without a critical influence. So we have to train this. We use the SNCF faults only. We will analyze it. This is the first simplification. We answer a simpler question. We want to train a model, go to the settings, and we want to handpick the parameters. So we go to the features, we select all, and basically reject them. And now we only will use non-technical features. So we take the hour and the calendar week, the week and all the weather data, so all non-technical parameters we will include into our model, and all technical parameter we will reject. So take this as input, and now we go to the algorithm, and we decide that we wanted to have a very selective algorithm, the third simplification, such that the algorithm really only concentrates on very few parameters. So now we used all this, we trained the algorithm, and once it's finished, we have an algorithm which can predict critical door faults and which can predict whether the door fault is critical or not. So this is done. And then we can use this algorithm. So first we apply the algorithm which predicts whether there is a fault or not. Then we filter it such that only trains with door faults remain, and then we use the second now trained algorithms to predict whether a train will have a critical or a non-critical door fault. So we're almost at the end of our little demo. Now, what can SNCF do with these two models? They can schedule them every half an hour based on the newest train data. So they get a warning 8 hours in advance if a door fault is predicted, and they get an estimate whether this door fault will actually influence the train's operation critically. So they have time to mitigate the consequences of door faults before they actually happen, and hence they provide to us a better train service. So I hope you enjoyed our little demo. Have a nice day. Bye bye.